On any given day in any given month, Paris' Charles de Gaulle Airport is a hive of activity, but more especially now during the high summer months. Today's date is August 2nd, 2005. With the time approaching 13:30 local, parked at Terminal 2 is Air France Flight 358, an Airbus A340-300 series aircraft, preparing for departure to Toronto's Pearson International Airport. On board will be a crew complement of 12, 2 cockpit crew and 10 cabin crew members, along with a booked passenger load of 297. For Air France long-haul flights originating from de Gaulle, flight crews meet at the flight planning room a minimum of 1 hour 45 minutes before the scheduled departure time. As part of their pre-flight preparations, the crew receive a flight planning package prepared by a flight dispatcher, which includes paper copies of all flight plans, operational notices, weather, etc. On foot of this, they continue to a dedicated briefing room where a detailed examination of this documentation is undertaken. This complete, the cockpit crew will then meet with their cabin colleagues, where the captain will specifically brief them on matters of operational importance, namely weather en route, turbulence, delay information, or technical defects which may have a direct impact on the cabin service. In command of today's flight will be 57-year-old veteran Captain Alain Rosset. He will have amassed over 15,000 hours of flying time, nearly 1,800 of which will have been gained on the A340 type. Accompanying him this afternoon will be First Officer Frédéric Naud, age 43. His total time will extend to almost 5,000 hours, 2,500 of which will have been found on the A340. Although the two men will have only crossed paths once previously during a routine simulator session, they will quickly strike up a positive interaction and set about their duties in a cordial and professional manner. Having reviewed the forecast weather for Toronto covering the hours immediately before and after their expected arrival time, Rosset will anticipate the possibility of inbound delays due to thunderstorm activity in the vicinity. As a result, his wealth of prior experience of similar situations will tell him to go prepared. In finalising his fuel load, therefore, he will decide to uplift an additional 3,000 kilos of fuel above and beyond the minimum required. To put this in context, this will allow the A340 to hold for an additional 23 minutes before burning into its alternate reserves. Under the circumstances, a prudent and sensible course of action. The A340-300 type made its maiden voyage back on the 25th of October 1991 and was certified for commercial passenger operation just over a year later. Entry into service came in March 1993 with both Lufthansa and Air France listed as launch customers. Being a fly-by-wire design, with its introduction the A340-300 continued what was by now a well-developed product, first introduced with production of the A320 back in the mid-80s. In a modification of the previous A330 fuselage, the 340 had a 3-leg main landing gear configuration in order to facilitate a higher maximum takeoff weight of 276,000 kilos. In length, this version of the A340 family extended to just under 64 metres, sufficient to accommodate between 250 and 290 passengers, with a range of 13,500 kilometres or just on 7,300 nautical miles. As improving engine reliability over the years will ultimately allow ETOPS operation for almost all routes, more economical twin jets will eventually replace the quads. And so 6 years from now, on the 10th of November 2011, with 380 aircraft having been manufactured, Airbus will announce that the production of the 340 family will finally reach its end. 10 years further again, and by 2021, the global A340 fleet will have completed more than 2.5 million flights, logged over 20 million block hours, and carried over 600 million passengers with not a single fatality. Of the 380 aircraft produced, by June of 2022, 207 will still be in active service across all continents of the globe. Manufactured in 1999, the aircraft in use today, servicing Air France Flight 358 to Toronto, will be the 289th of that 380 to roll off the production line in Toulouse. And so Golf Lima Zulu Quebec will take to the skies for the very last time. In just over 8 hours she will lie crippled and burning in a ravine close to Pearson International, and this video presentation will try to explain why. This is the full story of Air France Flight 358. Captain Rosset, having decided to complete the takeoff from de Gaulle as the designated pilot flying, will, somewhat unusually, ultimately delegate the handling duty to his first officer for the latter part of the crew's descent, approach and landing into Toronto. 358's flight plan for the ocean crossing will have the flight filed on North Atlantic Track Bravo, crossing the designated oceanic entry point off the Irish west coast at flight level 350, or the rough equivalent of 35,000 feet. The intention thereafter, as the aircraft burns fuel and becomes lighter, will be to climb to more economic levels of flight level 360 at 40 degrees west longitude, with a further climb to flight level 370 being planned at 60 degrees west. Before reaching their designated entry point, however, 358 will receive a revised clearance to expect track Alpha instead of Bravo. On the day, track Alpha will be designated as 1 degree of latitude or 60 nautical miles north of track Bravo, which will, although only marginally, actually extend the en route distance to destination. Of greater importance, however, will be the fact that, despite having planned for further climb along the route, adjacent traffic on the revised track will mean that further climb will occur later than planned at 1716 Zulu, and even then only as high as flight level 360 and not 370 as had been expected. Ultimately, flight level 360 will be the highest altitude attained throughout the flight. Although relatively marginal, these combined changes in circumstance will nonetheless have a detrimental impact on 358's fuel reserves and the resultant contingency planning. As the flight progresses and 358 enters the oceanic phase of the flight, at 13:51 Zulu, the crew will receive updated weather reports for potential en route diversion airfields along the northeastern Canadian coastline. Almost an hour later, they will again receive further updated weather reports, this time for their destination Toronto and their nominated destination alternate of Niagara Falls International Airport, just across the border in New York State. These reports, issued 45 minutes earlier at 1400 Zulu, will be largely unremarkable for either airport, with no reports of thunderstorm activity in either location. In addition to these actual reports, the crew will also attempt to obtain a new, revised and up-to-date forecast, but unfortunately this will prove unsuccessful. Later in the afternoon at 16:08 Zulu, the crew will receive the 1600 Zulu Automated Terminal Information Service Report, or ATIS, for Toronto Pearson. These reports, usually issued twice hourly, not only provide for the very latest weather update, but also facilitate arrival planning for the crew by indicating the runway combinations in use for departure and arriving traffic, as well as any specific notices which may be operationally significant. The ATIS received will indicate both good visibility and cloud cover with light surface winds. At 16:17 Zulu, crew handling duties, as agreed previously, will be reversed, with First Officer Node now assuming the role of pilot flying for the remainder of the flight. At 17:50 Zulu, just over 45 minutes later, 358 will send a message to Air France operations in Toronto. updating their estimated time of arrival to 19:39 Zulu, that being just after 3:30 in the afternoon local time. In reply, 3 minutes later, they will receive a message from operations with information regarding their eventual parking gate. Of significance, however, will be that in the interim since their last weather update, conditions at the airport will have started to deteriorate to the point where a red alert will have just been issued, although the content of the reply message to 358 will omit this important fact. In effect, a red alert is a highlighted alert message disseminated to all ground handling personnel at the airport, drawing attention to potentially dangerous weather in the locality. Under conditions of such alert, most ground operations will be suspended, including flight departures, although arrivals may still continue at the discretion of the individual crews. In other words, although the airport will remain open, unbeknownst to the crew, weather conditions at Pearson will have begun to change for the worse. In a subsequent testimony, the Air France station manager will state that as such an alert is specific to ground handling operations only, it was not company procedure, nor was it a regulatory requirement that the flight crew be informed. In retrospect though, had the crew been made aware of the red alert in effect, one can only surmise that their cognitive preparedness for what lay ahead would have no doubt been enhanced. At 18:49 Zulu, approximately 50 minutes before their planned arrival, the crew will again request and obtained an updated weather report for airports in the general Ontario area, including Niagara Falls, Ottawa, and Cleveland across the border in Ohio. Again, due to a selection error on their part, despite having also requested an updated forecast for the same airfields, this will not be received. Had they been successful in obtaining the updated forecast for Toronto, issued at 18:51 Zulu and valid from 1800 Zulu on the 2nd of August to 1800 Zulu on the 3rd, they would have seen that the overall outlook had become a lot more gloomy. Generally, over the period, the airport was forecast to experience relatively light northwesterly winds, with reasonably good visibility of 6 statute miles and a broken cloud layer at about 4,000 feet. Within this general forecast, however, there was included a cautionary note of expected thunderstorm between 1800 Zulu and 2000 Zulu, roughly the time frame when 358 was expected to make its approach. During this specific period, it was anticipated that temporarily visibility would reduce to 2 statute miles in moderate rain, with a corresponding reduction in the cloud base to 2,000 feet. Thereafter, conditions would slowly improve as the late afternoon and evening rolled in. At this point, the estimated fuel remaining will be approximately 12,200 kilos, with calculations predicting an estimated 8,700 kilos on arrival. This will facilitate a diversion to as far north as Montreal and as far south and west as Cleveland and Detroit. In light of the weather reports which will have been received, despite Niagara Falls having been initially filed as the destination alternate, the crew will now believe that conditions instead favour Ottawa and subsequently will calculate that 7,300 kilograms of fuel will be required in order to reach it. In light of the fuel reserve still remaining, this will leave a potential for 14 minutes of holding inbound to Toronto. At 19:03 Zulu, almost an hour before touchdown, Air France 358 will make initial contact with the Toronto Area Control Centre and inquire about the weather situation at the airfield. Without giving any detailed specifics, the controller will commit to providing them with updates if and when necessary. At about this time, a second message will be sent to Air France operations in Toronto, indicating that if a diversion is to become necessary, the decision has been made that they would be going to Ottawa. 10 minutes later, at 19:13 Zulu, a discussion will take place between the crew and ATC regarding the movement of the active weather. This discussion may have been prompted following the issuance of SIGMET Kilo 1, or a significant meteorological report at about the same time, and valid for the reporting period covering 358's arrival into Toronto. This report had made reference to the fact that thunderstorms had been observed 20 nautical miles either side of a line from 20 nautical miles west of Buffalo, New York, to 50 nautical miles southwest of Muskoka, Ontario. This broken line of thunderstorms was observed on radar, satellite picture, and by lightning detectors with the maximum tops of 44,000 feet. The line was reported to be quasi-stationary and not forecast to weaken until approximately midnight Zulu time, or 8 p.m. that evening. Subsequently, as a result of the developing situation at Toronto and the impact it will be starting to have on inbound delays, at 19:15 Zulu, 358 will be given instructions to reduce speed to the minimum possible in its current clean configuration. Almost coincidentally, the crew will request and be approved for track adjustments to circumnavigate weather up ahead. Finally, at 19:17 Zulu, 45 minutes before touchdown, the crew will receive their previously requested weather update for Toronto, which for the first time will definitively include information regarding thunderstorms and heavy rain in the area. Evidence of the crew's continued efforts at contingency planning will come at 19:19 Zulu, with review of the wind shear reaction procedure and their agreement that if encountered, they would immediately discontinue the approach. Shortly after, at 19:20 Zulu, Air France 358 will be advised by air traffic control to expect to hold at the enroute intersection, which they will enter into the aircraft's flight management computer. At roughly the same time, 358 will be informed that traffic has again started to move into Toronto and to expect further clearance at 19:50 Zulu, approximately 30 minutes into the future. Considering their fuel status, however, a delay of this magnitude will be problematic. Somewhat unexpectedly and very welcome, 5 minutes later at 19:28 Zulu, 358 will be cleared for the Simcoe 2 instrument arrival. The fuel remaining at this stage will be 9,300 kilograms, with the aircraft some 137 nautical miles or 254 kilometers from Toronto. In light of the changing circumstances, the crew at this stage will take the opportunity to review company and regulatory guidance on when it will become necessary to declare a minimum fuel condition. The concept of minimum fuel is a regulatory buffer to ensure protection of the ultimate final fuel reserve, that being 30 minutes endurance. In other words, a captain is obliged by law to make no operational decision en route which will deliberately have the aircraft land with less than 30 minutes of usable fuel remaining. That being the case, when reserves reduce to the point that the remaining fuel equates to that which would be required to reach the designated alternate, plus this final 30-minute reserve, he is under obligation to declare minimum fuel. What he's actually saying is that should there be any further delay inbound to destination and then subsequently he has to divert, the likelihood is that he will land with less than this 30 minutes final reserve intact. This declaration in itself entitles him to no preferential treatment over other inbound traffic, but does alert air traffic control to the fact that their fuel situation is becoming more critical. 3 minutes later at 19:33 Zulu, the ATIS information broadcast will indicate that Toronto is experiencing reduced visibility in thunderstorms and heavy rain, and rapidly changing weather conditions, with runway 24 left being the runway in use for all arrivals. At about this time, the crew will also receive further weather reports for Cleveland, Ottawa and Niagara Falls, with these updated reports endorsing their previous decision to use Ottawa as the most favourable destination alternate. Fuel reserves in light of this decision will now only facilitate a mere 6 minutes of holding fuel. In preparation for the approach, for the 4 minutes between 19:36 Zulu and 19:40 Zulu, a briefing will be conducted for the instrument landing system or the ILS approach to runway 24 left, in what will subsequently be identified as a significant turning point in their contingency planning. The brief failed to include any reference to the runway length or missed approach procedure, and critically, no runway distance calculations for a wet or contaminated surface will be calculated. In other words, the crew, having prepared for their approach into Toronto, will fail to calculate exactly how much distance will be required to bring their 340 to complete stop. And being the shortest runway of the 5 available at Pearson. Had they would have seen that the margins were incredibly small. Although certainly remiss from an airmanship perspective, unbelievably, the crew will be in breach of no company regulation, as Air France will, at the time, not require their crews to make any such calculations prior to landing. A casual review of non-standard misapproach procedures and runway length information will eventually be reviewed on the latter part of the approach, approximately 2 minutes before landing, but realistically, the crew will make no meaningful connection between the figures quoted and their application to the environment outside. What the crew had failed to appreciate was the fact that although a landing on 24 left was possible with the runway surface either dry or wet, the margins were only good in conditions of a headwind, or at least if the wind remained calm. Under calm conditions on a dry runway, an A340 weighing 185 tonnes, as was the case with Air France 358, using full flap and no thrust reverse on touchdown, would require 5,419 feet to stop, with medium order brake deceleration selected. This provided the aircraft crossed the landing threshold at 50 feet above ground level and carried no additional speed above the minimum calculated for the approach. Select auto brakes to the low setting and understandably the landing roll will increase under these conditions by a further 1,748 feet. Where the runway surface is reported as wet, which by definition is less than 3 millimeters of standing water, margins understandably are reduced still further, but given the runway length being 9,000 feet, not to any alarming degree. Where the figures do start to become alarming is where the environmental conditions give rise to a tailwind on touchdown. The A340 is certified to land with a maximum tailwind component of 10 knots. A review of the landing performance under these conditions, particularly with low auto brake selected, and the margins now start to look very tight indeed. In both cases, leaving only a couple of 100 feet to spare, and that again assuming that the aircraft touches down at the correct point on the runway and at the correct speed. In other words, the margin for error has been reduced to little or none. But in reality, what Air France 358 will actually encounter will be a whole lot worse. Some of it as a result of environmental conditions, some as a result of proficiency issues on the part of the pilot. With the approach briefing complete, 358 will again request an update of the Toronto weather and will be advised that aircraft are landing, but still there will be no prediction on their specific traffic flow situation. Acknowledging this message from ATC, the crew will again request to be kept advised of ongoing conditions, additional delays, and any worsening of the weather. Subsequently, at 1947 Zulu, the chief purser will be informed that, in the event of a diversion becoming necessary, the flight would be going to Ottawa. In parallel with the contingency plans being made on the flight deck of 358, other aircraft on the frequency will already have started to indicate their desire to commence diversion to the respective alternates. Some 2 minutes later, at 1949 Zulu, just 13 minutes prior to touchdown, 358 once again will request and receive a track deviation around weather on the approach. At 1953 Zulu, the number 1 aircraft on approach, Air France 358 being the number 3, will be asked by ATC about their likelihood of being able to land. They will reply that the weather's to the north and look pretty bad, but they believed that they would nonetheless be able to land. Subsequently, this aircraft, and one immediately following it, both land without incident. The investigation team could not ascertain for sure whether or not the crew of Air France 358 had actually heard this interaction. About the same time, the crew of 358 will complete the approach checklist and arm the approach mode, priming the aircraft's automated modes to capture the ILS's radiating localizer and glide slope signals, which will guide the 340 both laterally and vertically through the weather to the touchdown point ahead. As the crew commence reconfiguration of the aircraft for the approach, 358 will establish on the localizer, aligning itself with the extended centre line of the runway at a distance of 16 nautical miles or 30 kilometres. At this early stage of the approach, all will appear to be going according to plan. Reconfiguration will continue, with selection of flap 2 and extension of the landing gear, followed shortly thereafter by extension of flap 3 and full in sequence. The aircraft will decelerate to the final approach speed of 140 knots, while intercepting the ILS glide slope at approximately 8.7 nautical miles or 16 kilometers from touchdown. As the approach continues, at 19:58 Zulu, just 4 minutes before touchdown, the crew will be informed that the first of the 2 aircraft ahead of 358 have reported the braking action on runway 24 left as poor. Harping back to our discussion on landing performance, remember that the margins had already appeared tight on a wet runway. Well, typically wet runways with less than 3 millimeters of standing water don't give rise to poor braking conditions, and as such the report should have alerted the crew of 358 that perhaps things may not have been as they assumed. The tower's wind anemometer will not be operational at this time, having been knocked out 4 minutes earlier due to a lightning strike in the immediate area. Therefore, the last wind available, being supplemented by pilot reports, will be recorded as 230 degrees at 7 knots. Doing what they can, the crew of 358 will reselect the auto brace setting from low to medium, and the call-out commands for a potential go-around will be reviewed. Up to this point, they will have been very go-around minded and proactive with regard to fuel planning and management. This will make their failure to perform landing distance calculations all the more difficult to comprehend, particularly when these preceding aircraft will be providing all the necessary hints that things simply weren't right. Maybe one hypothesis is that the crew will be starting to succumb to cognitive continuation bias, where fulfilling the mission and landing on the runway ahead, come what may, has now become their overriding priority and focus. Symptomatic of their increased workload and no doubt developing tunnel vision is the fact that the landing checklist will be overlooked, although all items will in fact have been completed. The aircraft immediately preceding 358 will report a wind, as assessed by their onboard equipment, of 290 degrees at 15 gusting 20 knots, with the consistent braking action report of poor until reaching 60 knots ground speed on the rollout. So although the braking action reports will suggest that there is considerably more water on the runway surface than had been anticipated, at least they will still be driving into a modest headwind of 9 to 12 knots. As such, Captain Rosset will see no reason to alter his course of action, and thus will elect to continue with the aircraft's descent down the ILS glide slope. Weather conditions during the remainder of the approach will range from visual to instrument conditions, as the 340 enters and then breaks out of heavy, very dark cloud and rain. 358 will finally obtain visual contact with runway 24 left when the aircraft is about 2 to 3 nautical miles from the runway at an altitude of between 600 and 1,000 feet above ground level. The windshield wipers will have been turned to the slow setting at 4 nautical miles from the runway threshold and will stay on for the remainder of the approach and landing. From their vantage point, about half of the runway will be visible and at times part or all of the ramp area. What the crew will see is a runway covered with water, producing a shiny glass-like surface. There will be lightning on both sides and at the far end of the runway. The aircraft's weather radar will show heavy precipitation, with the red area encroaching on the runway from the northwest and another south of the runway. Compromised by the lack of wind information readily available from the tower, the flight crew will instead refer to their own navigation display, with the real-time wind display being computed by the onboard inertial systems. What will be concerning now is that the presentation will indicate that the wind has veered to an almost perpendicular crosswind from the right at 15 to 20 knots. As Air France 358 approaches 24 left, the 340's engaged autopilot will successfully keep the aircraft stabilised on the ILS localizer and glide slope, while the autothrust will maintain the approach target speed of 140 knots. At 20, 01 and 18 seconds, however, as the aircraft passes through 323 feet above ground level, First Officer Nude will disconnect both with the intention of completing the remainder of the approach and landing manually. Shortly after, an increase in engine thrust will be registered from about 42% N1, which is the engine compressor speed, to about 82% N1, as the first officer will subsequently testify that he was of the impression that the aircraft was starting to sink due to a sudden loss of airspeed. Upon later examination, the flight data recorder will in fact confirm this loss of speed, but also reveal that the application of power in response will cause the 340 to deviate above the ILS glide slope. Distracting as this will be for both crew members, what simultaneously will go unnoticed will be the fact that the wind direction has veered again, changing from a 90-degree crosswind component to an increasing tailwind component of up to 10 knots. Given the wind's sudden change in direction, if this tailwind component were to be maintained, the margin for error will, as explained earlier, become extremely small. In fact, if they are to experience genuine poor braking conditions, as have been reported by the two previous landing aircraft, then in truth it will have disappeared completely, even if they hit the expected touchdown point 1,000 feet from the threshold and accurately maintain the correct approach speed of 140 knots. At 20:01 and 39 seconds Zulu, the aircraft will cross the landing threshold of Toronto's runway 24 left. In crossing the threshold, it will, however, because of the power application moments earlier, deviate above the glide slope by approximately 40 feet. With Captain Rosset failing to articulate the deviation in flight trajectory, the excessive altitude which is being gained as the jet crosses the threshold will mean that it will now be almost impossible for the 340 to safely touch down at the correct aiming point on the runway, with the result that the landing will now inevitably be deep and any hope of stopping in the available distance most probably lost. But being in the dark as to what their margins had originally been to start with, neither crew member will identify the critical situation they were now in, and most probably the temptation to settle the aircraft onto the runway just feet below will be far more appealing than going around into a significant, fully developed thunderstorm off the departure end of the runway. And so, without in all likelihood making a conscious decision to do so, they will press on. Nude will begin to flare the aircraft at about 40 feet above the runway. From this point to touchdown, there will be numerous and sometimes significant pitch and roll inputs made on his side stick, with the aircraft actually levelling off at approximately 25 feet for a period of 2.5 seconds. Combined, these inputs will indicate that significant workload and attention is being required on the part of the handling pilot to control the aircraft. Continuing down the runway, the aircraft will almost immediately enter an area of heavy rain, where visual contact with the runway environment will become severely compromised, as lightning flashes all around them at 20:01 and 41 seconds Zulu, having allowed the airspeed to increase by 10 knots above the approach reference speed. First Officer Nude will retard the 340's 4 thrust levers to idle and wait for its 185-ton mass to settle onto the runway surface just below. Interestingly, despite the shifting wind, at no stage during the approach and landing will either the wind shear prediction or reaction systems trigger any alert to the crew. Some 7 seconds after the thrust levers are retarded to the idle position, the 340's 4 CFM56 5C4 engines will finally spool down completely. Floating further and further down the length of 24 left, the ideal touchdown point identified in the context of all these landing performance models will rapidly be left behind them. From a performance perspective, 358 will now be in a hopeless situation, which can only be rectified, even at this late stage, by termination of the approach and going around. According to the Airbus Flight Crew Operations Manual, standard calls during approach and landing require the pilot non-flying, in this case Captain Rosset, to call minimums as the aircraft arrives at the defined decision altitude for the approach. The pilot flying in response will either call landing or go around as appropriate. As such, it is the pilot flying who makes the call to continue or go around. The Air France Operations Manual at the time, however, differed in its instruction from that of the manufacturer, In Air France, the procedure was for the captain alone to assess whether to continue or terminate the approach, regardless of who was actually flying the aircraft, with the first officer being under obligation to suggest a go-around to the captain if he had serious reservations. This philosophy was not only at odds with the manufacturer's recommendation, but also with the procedures of most other carriers at the time, who believed that the best placed pilot to assess the likely success or failure of a potential landing was the one actually flying the aircraft at the time. Despite the fact that by now the decision had been made to continue to a landing, the Air France Operations Manual nonetheless provided the following additional guidance. After passing decision height, if the visual reference, the trajectory, or the position of the aircraft evolve in a fashion so as to compromise the successful completion of the approach and landing, the captain must initiate a go-around. 358 now most certainly satisfied these criteria, yet the only instruction noted on the cockpit voice recorder will be Rousset's direction to put it down, put it down. It's important to remember that a go-around or balk landing is an option that remains open up until the moment the reversers are selected. Once reversers are deployed, the committal is final. This, however, will not happen, and 14 seconds after crossing the runway threshold, Air France 358 will touch down at 20:01 and 53 seconds Zulu, approximately 3,800 feet into the 9,000-foot runway, almost 2,800 feet beyond the normal touchdown aiming point. With its extended float, the aircraft will touch down with just over 5,000 feet of the total 9,000 foot available in which to bring the jet to a stop. But it's not simply the deep landing which will challenge the crew as the rollout continues. The G-load on touchdown was measured at 1.17 G, a relatively smooth and highly desirable outcome on any other day, the sort of touchdown that passengers applaud. But in these conditions, with this amount of water on the runway, smooth touchdowns leave the potential for surface water to form an impregnable layer between the runway surface and the tyre itself. This phenomenon is technically referred to as hydro or aquaplaning. In exceptional circumstances, this wedge of water can actually penetrate the tyre contact area to the extent that the tyre footprint can be either partially or even totally detached from the pavement surface, in which case, no matter how hard the pilot applies pressure through the brake pedals, no deceleration is sensed between the tyre and the pavement. Furthermore, in assuming the runway to be simply wet, the crew will have anticipated conditions of 3 millimeters or less of standing water, but the reality, as alluded to by the previous landing traffic, will be considerably different. The investigation team would subsequently be of the opinion that rather than there being 3 millimeters of water on the runway surface, the actual figure was more likely 6 to 7 millimeters. As such, the runway was, by definition, flooded, and from a performance perspective should have been considered contaminated, and this comes with a reduced crosswind limitation of 15 knots. The reason for the reduced crosswind limit simply being that the greater the turning force exerted in maintaining directional control, the less efficient the ultimate braking force. In other words, the most efficient braking will occur with the aircraft travelling in a straight line over the ground. Introduce a crosswind, and the more the aircraft has to turn in order to counter its effects, the less efficient the braking process becomes, with the obvious consequences which that brings into play. The crosswind component at touchdown, although limited by certification to 15 knots, will actually be 19. And whereas the tailwind component was likewise limited by certification to 10, Air France 358 will experience 12. So despite all the contingency planning, 358 will cross the threshold high and fast, and as a result land deep, very deep, on a contaminated runway and outside of the certified limitations for the 340 in both crosswind and tailwind. In short, the landing performance model will now have changed so drastically that 358 will be in a place that no one could have planned for, and the maths will tell a chilling story. Looking at the landing performance now in the context of what the crew will actually experience reveals just how desperate their situation will become. With the estimated tailwind component at touchdown being 12 knots, reducing to 10 knots by the time the aircraft will reach the end of the runway, and standing water assumed to have been between 6 and 7 millimeters in depth rather than the initial 3. If 358 applies maximum braking on touchdown, with simultaneous application of full reverse on all 4 engines, then the aircraft will overrun the end of the runway by nearly 1,250 feet. This will be the best possible outcome which can be achieved, assuming of course that the aircraft will touch down at the correct point on the runway and at the correct speed, which as we now know will not be the case. On the latter part of the approach, reports of poor braking action went unheeded by the crew, with the potential implications being completely overlooked. With the tailwind and standing water combination which now existed, 358's fate will be sealed no matter where on the runway it will finally touch down, and as such, the inevitability of an accident is now certain. On touchdown, the right main landing gear will be slightly left of the runway centerline and the aircraft will crab about 6 degrees to the right. The spoilers will deploy automatically per design after the main wheels contact the runway. First Officer Nude will then immediately apply maximum manual braking and attempt to align the aircraft with the runway centerline. Idle reverse will be selected almost 13 seconds after main gear touchdown, with full reverse being selected just over 3 seconds later again. When later queried on system functionality, Airbus confirmed that the A340 aircraft flight manual uses approximately 5 seconds between landing gear touchdown and thrust reverse selection, and a further 1 second for the reverser deployment as the benchmark for calculating stopping distance. 358 will take approximately 2.5 times as long to achieve those standards, introducing yet another variable to compromise their performance. Most probably as a result of being distracted by what he will be seeing outside of the cockpit, Captain Rosset will fail to make the standard callouts in relation to spoiler and thrust reverse deployment, potentially leaving Nude unaware of his oversight. The aircraft will be unable to stop on the remaining runway, and at 20:02 and 18 seconds Zulu, 26 seconds after touchdown, will depart the paved surface at a speed of 86 knots or 159 kilometers per hour, coming to rest in a ravine off the end of the runway. As it leaves the paved surface, the tailwind component being experienced will have reduced slightly to being just on the limits at 10 knots, with the crosswind component stubbornly remaining outside the aircraft's stated limits, as it had been since touchdown. At this time, 3 or 4 bright orange flashes were observed from the control tower through the heavy rain. The crash alarm was thus activated at 20:02 and 45 seconds, 24 seconds after the aircraft had left the runway. A group of firefighters who had been in the alarm room of the South Fire Hall adjacent to runway 24 left actually witnessed the events unfold and mobilised themselves even before the alarm was raised, and in so doing ensured that the first response vehicles were on scene within 60 seconds of the crash happening. From the time the aircraft left the runway until it came to a stop in the ravine, it bounced violently and repeatedly, and there were a minimum of 3 distinct impacts. On each impact, cabin occupants were propelled upwards from their seat, their arms and legs flailing. Simultaneously, they were subjected to longitudinal decelerating forces, and some reported hitting their heads on the seatbacks in front of them and/or the cabin sidewall panels. During this time, the cabin crew didn't instruct passengers as to what actions they should take relevant to the emergency situation at hand. That is, they did not instruct passengers to assume any brace for impact protective positions. European regulations at the time did not require such brace commands and therefore did not require any recurrent training in the event of an unexpected accident. Therefore, not surprisingly, Air France's emergency procedures for cabin crew outlined no requirement to shout brace commands in the event of an unexpected accident, as opposed to a prepared emergency landing. This fact was at odds, however, with both Canadian and US regulations, where cabin crew were instructed to shout brace commands at the first indication of a potential accident. It's estimated that approximately 15 to 20 seconds elapsed between the time the aircraft departed the runway hard surface and it coming to a stop in the ravine. It appears that during the impact sequence, the regular lighting system in the cabin went out, the emergency lighting system came on, flickered, and then went off in some areas of the cabin while remaining on in others. The floor escape path lighting system was not on in the aisle leading to the fore right emergency exit during the subsequent evacuation. Photos taken by passengers inside the cabin during the evacuation, however, did confirm that the ceiling exit sign adjacent to the to left exit was lit. The emergency lighting in the forward cabin most likely failed at the same time as the PA system. When the aircraft came to a full stop, the chief purser in the front of the aircraft released his seatbelt and retrieved the PA handset from the floor, as it had been knocked from its cradle during the overrun. He wasn't aware of any smoke or fire from where he was standing, nor did he know that many passengers were already in the aisles making their way to the emergency exits. He made a direct PA stating, "Everything is okay, remain seated, the crew will look after you." The junior purser then arrived and told him that there was a fire by door 3 left and that an evacuation was required. The chief purser turned and faced the cabin, seeing fire outside the aircraft through the windows on the left side of the fuselage. When the captain was advised of the fire and the need to evacuate, as per the flight crew's emergency procedures, he pushed the cockpit evac push button to activate the evacuation alert system. However, the system failed to respond due to the loss of all electrical power. Instead, the cabin crew members each individually activated the alert from their positions at their respective duty stations. Importantly, another significant effect of the lost power was the crew's inability to communicate with ATC or the airport's firefighting personnel. In a post-accident safety questionnaire, passengers were asked to report on visibility after the aircraft came to a stop. In all, 20% of respondents reported that from their seats they could see only a few rows around them. 14% reported that they could see only a few seats around them. Thus, it was established that although it was somewhat dark in the cabin, the ability of the passengers to evacuate wasn't compromised by insufficient lighting. Fire was observed on the left wing through door 2 left, which had unbelievably opened by itself prior to the aircraft coming to a complete stop, and through the viewing portholes in both the cabin doors at doors 3 left and 4 left. 42% of passengers who responded to the post-accident safety questionnaire saw flames on the outside of the aircraft while it was still moving, and 10% saw smoke in the cabin before the aircraft came to a stop. It was believed that black smoke first entered the cabin from the left side of the aircraft, just below the windows in the area of passenger seat rows 29 and 31. When the aircraft came to a stop, smoke continued to enter the cabin, making it difficult to see during the evacuation, with the cabin crew member at door 3 left, whose station was just aft of row 31, being forced to don a smoke hood for her own personal protection. Despite this, it was established that there was no actual fire in the cabin during the evacuation itself. While exiting his seat with difficulty, First Officer Nude got a flashlight and went to the rear of the aircraft with the chief purser and one of the cabin attendants, checking to see if there was anyone left in the cabin or any of the lavatories. They returned to the front of the aircraft via the opposite aisle, confirming that the cabin was completely evacuated before they left the aircraft via door 1 left, from which they had to jump because the slide had only partially deployed. Node was the last person to exit the aircraft. The captain had also attempted to check the aircraft for passengers before exiting, but was forced to turn back due to dense smoke. He left the aircraft with difficulty through door 1 right as a result of a back injury he had sustained on impact. The evacuation continued during heavy rain, with thunderstorms being reported in the area from about 1900 Zulu until at least 2020 Zulu, when the rain finally started to abate. Most passengers appeared to be coming up the embankment along the right-hand side of the aircraft, while others were scattering in both directions along the creek. One passenger with a broken leg was found in this area adjacent to the aircraft. The steward seated at door 3 right and an airport employee remained with the passenger until a team of firefighters were able to assemble and carry the passenger up the hill on a backboard, with this individual being the only passenger to require specific assistance from the rescue personnel. Entry was gained to the aircraft interior at the front cabin door. The flight deck and the first 6 rows of passenger seats were checked for survivors, but the firefighters were ordered to evacuate from the aircraft due to the increasing risk being posed by random explosions outside. At the onset of the evacuation, exits 1 right and 2 right were assessed by the cabin attendants as unusable because the creek was immediately outside the exits. Both attendants followed the prescribed procedure for unusable exits, while redirecting passengers to other exits which were available for use. As the evacuation progressed, however, the same attendants were forced to reassess this original decision and conclude that they would have to use them to expedite the evacuation in light of the ever-increasing amount of smoke entering the cabin. The door was thus opened and the slide at door 1 right deployed per design. However, the angle of the slide, once deployed, was very shallow, being almost perpendicular to the aircraft. This had the undesirable effect of slowing the rate of passenger egress. At the bottom of the slide, vegetation on either side of the deployed path pushed against the slide, causing it to curl inwards, forming what was described as a tube. At one point, the cabin crew member attending the door had to stop the evacuation to wait for passengers already on the slide to pass through this tube. As more passengers used the slide, the bottom of the slide finally flattened out. The junior purser positioned at the open door 2 left knew immediately that the exit was unusable because of the fire outside and the fact that the slide attached to the door had failed to deploy. It was he who had gone to the chief purser in order to report his observation of conditions in the cabin, actions which most likely enabled the evacuation to begin sooner. In so doing, however, he had not had time to reclose his door and had left the open exit unattended for an undetermined period of time. In his absence, at least 16 passengers egressed through it. 2 of the passengers incurred serious injuries, one when he jumped from the exit at a height of 10 to 12 feet, and the other when pushed out of the exit by other passengers. The junior purser subsequently returned to his door and redirected passengers to the door at 1 left instead. The slide on this door had only partially inflated, and given the nose-down, left-wing high attitude of the aircraft, this meant that the slide came to rest folded in half against the fuselage, so that when passengers jumped from the exit, some became trapped in the folded portion of the slide and were unable to extricate themselves before others jumped on top of them. As this continued, the slide eventually deflated completely as a result of 2 separate punctures. The cabin attendant at door 3 right assessed the exterior conditions using the viewing porthole in the door, but didn't see any indications of fire below the exit or wreckage in the slide deployment path. Despite this assessment, when the door was opened, although deploying automatically, the slide immediately deflated on contact with debris outside, rendering it also unusable, but at the same time allowing smoke to enter the cabin. Per the airline's procedures, the door was subsequently closed and the attending cabin crew member redirected passengers to an alternative exit. It's interesting to note, however, that despite the cabin crew member's best effort to ensure the safety of the passengers, 2 individuals physically forced their way past and jumped from the exit itself. It isn't known what, if any, injuries they subsequently incurred. Fire outside the aircraft rendered emergency exits 3 left and 4 left unusable. The cabin attendant stationed at 3 left blocked the unusable exit and redirected passengers to the nearest available exit as per the operator's prescribed emergency procedures. The aft purser stationed at 4 left emergency exit didn't block the unusable exit, as it was evident that the exit couldn't be used because of the fire on that side. The 4 right door was difficult to open, requiring 2 cabin crew members to lift the door control handle to the fully up position and push the door out. Once outside of the door frame, the door did, however, move forward easily. It appeared to the cabin crew that the pneumatic system utilised to assist with the door opening in emergency situations had failed to engage, although this perception was later dismissed on foot of further investigation. Approximately 1 door width forward of 4 right was a permanent fold in the outer fuselage skin, indicating that the location had been subjected to a substantial bending force on impact. This deformation of the fuselage was very likely transmitted to the door frame, and it was this which had actually impeded the opening of the door. In total, therefore, 4 of the 8 emergency exits were unsafe for use or unusable. Approximately 2/3 of all passengers evacuated via the 4 right exit. The remainder evacuated via exits 1 left, 1 right and 2 right, with a few evacuating through exits 2 left and 3 right, with an estimation that the aircraft was completely evacuated in a little more than 2 minutes. In their summary, Transport Canada noted that approximately 49% of passengers attempted to take their carry-on baggage with them. In one instance, when a cabin crew member told a passenger that she couldn't evacuate with her baggage, another passenger responded, "Don't pay any attention, we have enough time." In a second case, a cabin attendant noted that a passenger blocked egress while retrieving and arranging items of his carry-on baggage. The passenger did not respond to the attendant's commands to leave his baggage behind, nor did he respond to the angry comments from passengers standing behind him. Consequently, the cabin crew member was forced to redirect passengers through the middle bank of seats to the other side of the aircraft in order to assess the only available exit in the aft cabin. This in view of the urgency to egress rapidly, because of the smoke in the cabin and the fire outside, they believed, presented a significant and obvious risk to safety. An updated weather report was issued at 2000 Zulu 2 minutes before the accident. It referred to winds 290 degrees true at 11 knots, which would have given rise to a 4-knot headwind on runway 24 left, with a 10-knot crosswind, which is more representative of what the crew thought they would be facing into. With that, there was a report of 4 statute miles visibility in heavy rain and thunderstorms. General remarks following the report made reference to towering cumulus all across the local area, with cloud-to-cloud lightning visible to the southwest and northwest. But as 358 was on approach at the time, they never received this report. Indicative of just how quickly conditions had changed, just 4 minutes later and 2 minutes after the accident, a special weather observation had been released. It referred to the wind having veered to 340 degrees true at 24 to 33 knots, with visibility of now only 1.25 statute mile in heavy rain and thunderstorms. What had been a modest headwind and manageable crosswind only 4 minutes earlier had now veered into a tailwind component of between 10 and 13 knots and a punishing crosswind from the right of between 23 and 31 knots. Even had the landing been flawless, 358 on that runway under those conditions didn't stand a chance. As the investigation into the events of that afternoon continued, the meteorological radar station located at King City, some 33 kilometres north of the landing runway, was used to analyse the thunderstorm activity and the specific weather the crew of Air France 358 had experienced. King City is the closest weather radar to Toronto's Pearson International and was capable of scanning to as low as 280 metres or just under 600 feet above the runway surface. What this analysis revealed was that at the exact time of the accident, there had been a downburst approximately 8 kilometres to the northeast, and given the direction of the wind at the moment of touchdown, the presence of such a phenomenon in the adjacent area may well have been a contributing factor. In short, a downburst is a concentrated vertical column of air which falls from a developed thundercell. Not only is flying through such a phenomenon potentially very dangerous, but as the column contacts the ground and spreads out in all directions, the sudden wind shear which this produces can likewise be hugely detrimental to aircraft performance. As the rain pounded the airport, later analysis would also be able to quantify exactly how much water was actually falling at the time. Records showed that for a 13-minute collection period, commencing at 1955 Zulu, just 7 minutes before the accident, an average of 1.6 millimetres of rainwater was settling on the runway surface every minute, and that being the case meant that anything up to 10 millimetres of water may have been standing on the surface of 24 left as 358 touched down, more than enough to have made a safe landing and rollout simply impossible. There was significant lightning activity in the vicinity of the runway late in the approach. Another analysis of the cloud-to-ground lightning strikes that could have intersected the flight path of the aircraft was conducted using recorded lightning strike information. The analysis showed that at approximately 2017 seconds Zulu, with the aircraft ascending through approximately 1,000 feet, there were 6 cloud-to-ground lightning strikes in the area of the runway threshold. At 20:01 and 20 seconds, when the aircraft was approximately 400 feet above ground level, there was a group of 5 cloud-to-ground strikes abeam the touchdown zone to the left of runway 24 left. 7 at approximately 20:01 and 49 seconds within a 1 second period, and 5 seconds before touchdown there was a 9 cloud-to-ground lightning strikes off the end of the landing runway. These numbers are likely a conservative estimate of the number of lightning strikes actually visible to the crew, since they only account for cloud-to-ground lightning strikes that could have intersected the approach path. Although there was no record or evidence of 358 having been hit by lightning, there's no doubt whatsoever that the vista visible through the forward windshields of the 340 as it closed in on the last remaining miles before touchdown would have been terrifying, even for the most experienced of crews. But why had Air France 358 found itself here in the first place? An earlier human factors study conducted at the Massachusetts Institute of Technology may provide some answers. It was concerned with identifying the factors which contribute to the decisions of flight crew to penetrate convective weather. The value of the study in the context of Air France 358 was that its findings conclusively demonstrated that flight crews were disposed to flying into convective weather when entering into a terminal area for landing, while at the same time would proactively avoid such action during the en route phase of flight. What was observed was that pilots were more likely to penetrate significant weather when they were closer to the destination airport, when they were closely following another aircraft that already penetrated the storm, when they were more than 15 minutes behind schedule, and where the landing was being conducted during the hours of darkness. To put their finding into context, the number of storm penetrations en route was observed to be minuscule when compared to the number of reported penetrations in the terminal area close to the destination airport. In attempting to rationalise the reasons why, the authors of the report propose that thunderstorms may in fact be harder to detect for aircraft that are landing, given that they are flying low, often in congested airspace, where workload, ground clutter, and frequent turns make it more difficult to make effective use of the onboard weather radar. Also, assuming that crews were able to detect the weather, avoiding it in terminal airspace incurs a greater commercial cost than avoiding weather en route. As such, deviation may often culminate in a missed approach or the necessity to initiate a diversion to an alternate airfield. In general, it's fair to say that crews are focused on reaching their destination, and as such, diverting the flight is viewed as being in direct conflict with this specific goal. Finally, it's a statement of fact that pilots in the terminal area have fewer options to deviate around weather due to traffic density and the confines of the approach itself. The findings of the study also established that aircraft penetrations of heavy precipitation returns in the terminal area often incurred no adverse consequences, strangely meaning that the more often a pilot did it, the more likely he was to keep doing it, in effect normalising this risky behaviour. When you compare the different rates of penetration between en route and approach, it's clear that pilots are aware of the risks associated with such penetrations and will by choice avoid penetrations where possible en route, but at the same time display a willingness to accept these risks as they enter the landing phase. Although the presence of heavy precipitation on radar screens is often insufficient to convince pilots not to enter a particular area, once one aircraft breaks off the approach or another piece of information becomes available to indicate that it may not be a good idea to continue, the study showed that the following crews were much more likely to terminate the approach or avoid the same convective weather in the first instance. In their final analysis of the crash of Air France 358, Transport Canada concluded that all aircraft systems were serviceable and working as designed throughout the approach and landing. Therefore, a mechanical malfunction was deemed not to have been a contributing factor. In hindsight, the risk presented by the rapidly deteriorating weather conditions was greater than most pilots would have deemed acceptable. However, when the crew of 358 assessed the available weather information and the traffic flow into Pearson, they did not expect that such a severe deterioration in the weather was immediately imminent. While en route, although the pilots were not receiving updated forecast information for their destination or alternates, these updated reports hadn't changed appreciably. Therefore, it's unlikely that they would have altered the crew's decision-making process, even if they had been received. As they came closer to Toronto, Rosset and Nude were concerned about the thunder shower activity at destination. Initially, their concern was focused more on the approach delays which these showers might give rise to, rather than on the potential for the thunder shower activity itself to adversely affect the flight during the approach to landing. They were not alone in this thinking, as several other aircraft were making the same assessments and judgments about the delays and weather conditions. Some crews chose to divert, while others decided to continue. And while Rosset had decided to press on, he was nonetheless mindful of the need for a contingency diversion plan, with evidence suggesting that he continued to closely monitor their fuel reserves to ensure that they had enough to divert to Ottawa if necessary. Despite this continued evaluation, there's no indication that the crew's management of such contingency planning became so focused as to cause them to lose sight of the bigger picture. However, that said, in the context of their overall situational awareness, regrettably, there's also no indication that the crew of 358 specifically made any calculations in relation to the aircraft's landing performance. Indeed, it would appear that the potential impact of a rapidly changing environment on this landing performance simply hadn't been accounted for. The events surrounding Air France 358 clearly shows the need for pilots to know the landing distance required by their aircraft for the conditions to be encountered at the expected time of landing, and to compare these figures to the length of the runway assigned for the landing itself. It's essential that both figures be known to enable crews to calculate the margin of error available so that they are better prepared to make the correct decision when they encounter deteriorating conditions. In this occurrence, the CVR clearly records Rosset instructing Nude to put it down, indicating that he at least was aware that the landing was going to be long. Under the circumstances, therefore, had the captain known that the margin for error was slim or indeed non-existent, then presumably he would have terminated the approach and executed a go-around, thus mitigating the possibility of an accident in the first instant. In making such a significant observation, however, it must also be stated that unbelievably, Air France at the time did not require their crews to make such an assessment before commencing the approach. Indeed, upon examination, it was later proven that when using the existing Air France documentation, the methodology behind the application of these calculations was ambiguous and could often produce inconsistent results. As the approach continued, both pilots knew that the weather near the runway would be affected by the nearby thunderstorm activity. However, they assessed that their safety margin hadn't been unduly compromised. They briefed the wind shear procedure and were prepared to initiate an immediate go-around in the event that they had received a wind shear alert. In so doing, their decision to continue with the approach to 24 left was consistent with normal industry practice, in that they could continue with the intent to land while maintaining the option to break off the approach if they assessed that the conditions were becoming unsafe. It's an established fact that once individuals select a particular course of action, it takes very compelling cues to alert them to the advisability of changing their plan. Having made their decision to land, Rosset and Nude used all of their energy to concentrate on this task and miss cues that should have warranted a review of that decision. The investigation board believed, therefore, that the crew's ability to capture and interpret cues that were essential in the decision to land process was inadequate, especially when the cues were ambiguous or not immediately compelling. Consequently, they continued to land in deteriorating weather once the landing decision had been made, in spite of cues that indicated that termination of the approach would have been a far wiser and safer course of action. Until the decision height of 200 feet above ground level, the aircraft was stabilised, although an airspeed increase and a deviation above the glide slope were beginning to occur around this height. Although good airmanship would dictate otherwise, below this height, Air France procedures at the time didn't mandate that the PNF, or the pilot non-flying, in this instance Captain Rosé, was obliged to highlight such deviations. The point at which the situation changed from normal and manageable to abnormal and critical was near the runway threshold, when the aircraft entered the perimeter of the thunder cell activity. At this time, a number of circumstances combined, leading directly to the accident. First Officer Nude, as pilot flying, was monitoring the airspeed trend vector and responded to an indication of decreasing airspeed by adding power. However, this application of additional thrust was maintained for too long, resulting in an excessive increase in airspeed, which addressed the immediate problem, but also generated increased lift over the wing and the aircraft's subsequent deviation above the ILS glide slope. The manufacturer stated that had the autothrust been engaged, the engine power would have been adjusted to maintain the proper airspeed and would have been more likely that the aircraft would have been landed closer to the target touchdown point. At that very moment, both pilots became preoccupied with the reduced forward visibility, and as a result, their monitoring of the airspeed condition was compromised. As they crossed the runway threshold, with the heavy rain, low visibility and lightning, the flight crew members, overwhelmed by the severe weather conditions, became task saturated, making a normal landing incredibly more difficult. With their attention focused outside the aircraft, neither noticed that a shift in the surface wind was also occurring at the very same time. While they were in the flare and floating just above the runway surface, the crew of 358 failed to appreciate exactly how much of the runway was being used up, and having not previously calculated the aircraft's actual landing performance, had no appreciation of how the previously small margins had literally disappeared. Their surprise at the rapidly changing and unexpected conditions may go some way towards explaining the slow reaction time of First Officer Nude in reducing the engine power to idle. The flight data recorder readout showed that at touchdown, the aircraft wasn't aligned with the runway centerline due to the developing crosswind. This crabbing effect would have consumed much of Nude's cognitive capacity as he became fully occupied with controlling the aircraft. Again, proof of the challenges he was facing and the cognitive saturation it was giving rise to was his significant delay in deployment of the jet's thrust reversers. Although not handling the aircraft at the time, Rosé too demonstrated the effects of fixation in failing to make the standard PNF calls after touchdown in relation to spoiler and thrust reverser deployment. Arguably, had these calls been made at the appropriate time, highlighting the fact that deployment of the reversers had not occurred, perhaps Nude may have been prompted into action earlier. But even if the thrust reversers had been deployed, it's unlikely that Nude would have selected full reverse in the early stages of the rollout, because Air France procedures, in accordance with the manufacturer's flight crew operations manual, called for reverse thrust to be reduced if the aircraft is not aligned and or is drifting off the centerline in crosswind conditions. The manual states that under such circumstances, failure to do so may have the undesirable effect of actually aggravating this misaligned condition. Why this is important is that the delay in selection of the thrust reversers and the subsequent delay in the application of full reverse thrust added to the landing distance needed, although in truth, even accurate execution would not have prevented the excursion. It was fundamentally the condition of the runway's surface which impacted the braking action available. As a statement of fact, at the point where the aircraft finally touched down, for contaminated runway conditions, there simply wasn't enough runway remaining to bring the aircraft to a stop. Indeed, even if the runway had simply been wet, the increased tailwind component and deep landing meant that there was only ever going to be one outcome, and an overrun was inevitable. The option of executing a missed approach exists up until the thrust reversers are deployed, meaning that such a termination of the approach is still possible even after touchdown. However, in analysing the crew's thought process, as the aircraft approached the threshold of 24 left, in the presence of ominous thunderstorms and lightning strikes visible on the missed approach path, the crew appeared to commit to the landing, in the belief that given the weather ahead, Their option to go around no longer existed. Despite the risks associated with these hazards, both research and previous accident investigations have shown that the penetration of convective weather in terminal areas during approach to landing is an industry-wide practice. The same research shows that aircraft most often deviate around convective weather outside the terminal area where there are more options available. Therefore, pilots are aware of the hazards presented by convective weather, but regularly determine that the risks associated with flight into convective weather is acceptable to facilitate landing at the destination airfield. The nature of convective weather and the quality of information available to crews to assist in assessing the risks associated with the convective weather make it difficult to obtain a clear picture of the actual level of risk associated with a particular storm. In fact, convective weather has all the factors associated with an increased probability of decision errors, as seen in previous studies of pilot decision making. Convective weather is dynamic, and many of the most significant hazards described previously occur rapidly and with little warning. Furthermore, much of the information available to the flight crew is ambiguous, in that it only provides indirect information with respect to the individual hazard. While heavy precipitation returns are associated with all the hazards of convective weather, one can often see heavy precipitation returns without experiencing any hazards at all. Therefore, multiple sources of information must be combined to make a judgment about the actual risk at the time and to project what the weather will be like in the future. This judgment can easily result in an underestimation of the risks involved. The likelihood of underestimating the risks associated with convective weather increases with each successive encounter, particularly where there's no adverse consequences experienced. In other words, the more often pilots penetrate thunderstorms without experiencing any adverse effect, the more likely it is that they will normalise the practice and continue to do so in the future. Furthermore, such decisions, continue or divert, are often made in the face of competing goals. The decision to divert based on ambiguous information in a highly changeable situation may be difficult commercially for the crew to justify. During the approach, the crew of Air France 358 were receiving information that clearly indicated that there was significant weather over the airport. The weather radar was showing red areas close to the runway. There had been 2 reports from preceding aircraft that the braking action was now poor, and looking forward, the crew could see for themselves lightning in the vicinity of the airport. In such circumstances, Air France procedures stipulated that, in the absence of any measured coefficient of braking being available, a report of poor braking was to be interpreted that the runway was contaminated. The principal threat to which Air France 358 was exposed was the forecast convective weather at the planned time of arrival into Toronto. This threat was mitigated by the crew's decision to upload an additional 3 tons of fuel, which would allow the aircraft to hold for approximately 23 additional minutes. And given the normally transitory nature of thunderstorms, the crew felt that this was an adequate measure. It wasn't until very short final that there were clear indications available to the crew that the flight had progressed to a point where landing was not advisable. The crew themselves in post-accident statements remember the runway surface as being shiny, like the surface of a lake. This, combined with the aircraft's subsequent deviation above the glide slope, while simultaneously entering an area of intense precipitation and reduced visibility, left the crew with 2 potential courses of action. Firstly, proceed with an approach that was becoming increasingly difficult, or secondly, conduct a missed approach into potentially dangerous conditions. At that moment, although Air France procedures called for a go-around any time the ideal trajectory was not being maintained, the captain, doubting that a go-around could be conducted safely, committed to the former and continued with the landing. In advance of the accident, Air France had already identified the potential for a weather-related landing accident, and thus had made this a particular focus of its flight safety program. The primary action taken by the company in this regard was to practice and encourage go-arounds any time prior to the deployment of the aircraft's thrust reversers. Whilst this goes some way toward addressing the risk of this type of accident, it does not completely address the problem faced by a crew approaching into convective weather and the hazards particularly associated with these types of conditions. Whilst these phenomena are possible with any thunderstorm, they are not present with all thunderstorms. As was the case in this occurrence, conditions can change very quickly, with one aircraft encountering manageable conditions on approach and the next experiencing quite different conditions altogether. From the crew's portion of the flight, Air France, like other airlines, has clear guidelines as to how far the aircraft should be operated from convective weather. Although crews are still required to exercise some good judgment in these situations, they have some clearly established best practice to follow. However, for the approach and landing portions of the flight, no such guidelines existed at Air France and many other airlines at the time. Where guidance is provided by some operators, it often comes in the form of directive in relation to approaches around thunderstorms. It's argued that the benefit of such mandated guidance ultimately assists the crew in making decisions in situations where the choices before them are less than obvious and clear-cut. Such guidelines and directives have been embraced so as to minimise the impact of operational pressures, stress and fatigue on the decision-making process. Therefore, statistically, in the absence of clear guidelines with respect to the conduct of approaches into or adjacent convective weather, evidence would suggest that there is a greater likelihood that crews will persevere and continue with the approach, with the focus being on ultimately landing at destination. Indeed, that was the case in the afternoon in question. 4 aircraft had landed on runway 24 left in the 10 minutes immediately prior to 358's arrival, with 1 additional aircraft on approach behind them. As with 358, these crews had also elected to conduct their approaches in conditions similar to those encountered by Rosé and Nud. At 9:50 Zulu, approximately 12 minutes before the accident, Rosé and Nud had indeed observed red on their radar display near their intended approach flight path and yes, had decided to continue the approach with caution. This may be seen as an operational decision error through the framework provided by the threat and error management model, with the decision undoubtedly increasing the risk to which the flight was exposed. However, the continuation of approaches into convective weather, as we've seen here, is widespread throughout the industry, and the crew members did take action to mitigate the threat by reviewing the wind shear recovery procedure and discussing their flight path in the event that a missed approach became necessary. They discussed where the cells were located and planned to turn left and go in between 2 observed cells if they had to overshoot. The above is an indication that, at 1950 at least, the crew of Air France 358 still believed that an aborted approach could be safely conducted if continuation became impossible. During the late stages of the approach, the general threat of convective weather, which the crew had been anticipating and taking action to mitigate throughout the flight, began to manifest itself as more specific hazards. At the time, although the combination of these hazards was ominous, it was not sufficiently compelling to the crew to warrant breaking off the approach. Specifically, the threats which could have been identified were a significant crosswind, reports of poor braking action, and reduced visibility due to heavy rain and lightning. The crew took action to address 2 of these items individually. Firstly, the auto brakes were set to medium to account for the runway surface condition, with the captain discussing the need for a positive touchdown on the wet runway, and secondly, he, as the pilot non-flying, would monitor the winds and advise the first officer accordingly. As such, crew coordination throughout the flight and the initial part of the approach was reasonably effective. Significant threat management behaviour was observed on the part of the crew, and errors observed were trapped or largely inconsequential. The overall risk to which the flight was exposed, however, increased during the latter stages, with additional exposure to the threats of reduced visibility and a crosswind tailwind component. It was thus the crew's inability to anticipate and subsequently respond to these developing threats, which ultimately led to the various proficiency errors which culminated in the aircraft's deviation above the ILS glide path. As such, it can't be said that the crew's underestimation of the hazards associated with the thunderstorm at the airport can be attributed to inadequate interaction and communication, but rather one would have to say that their judgment to continue may well have been significantly influenced by their own prior experience in such circumstances in the past. In other words, they had done as much as they believed necessary to mitigate the adverse environmental factors, as they no doubt probably had many times in their careers beforehand, and all had worked out fine. It's conceivable, therefore, that their experience of the past had now biased their expectation of the future. Yet again, however, it has to be stressed that 358's decision to continue under such circumstances and pilots' general behaviour in normalising such action in light of favourable past outcomes is not in itself uncommon. Investigations into accidents similar to this one, along with very well thought out conclusions, findings and recommendations, have not made much of a dent in the overall numbers of such accidents which continue to happen around the world. In fact, in the 5 years immediately preceding the loss of Air France 358 in Toronto, 20 such accidents to large commercial operators had been recorded. This is worrisome because it is a clear indication that, in spite of the efforts of all concerned, and although we are learning from these accidents or the experiences of others, we seem unable to develop adequate tools to mitigate this specific risk. Events that were commonly observed in some or all of these accidents were typically crews who had been on approach behind or in front of other aircraft that were landing or intended to land. Thunderstorm activity or monsoon storms were either fast approaching or actually over the landing area while the aircraft was on approach. The presence of heavy rainfall was a common occurrence. This resulted in the runway often being contaminated with water, where poor braking action was either reported by previous aircraft or was experienced by the crews of the accident aircrafts themselves. In many instances, there was a strong crosswind or tailwind component, or indeed a combination of both. Likewise, in many cases, the aircraft deviated from the target speed and or glide slope on short final. Often there was a wind shear, perhaps associated with downdrafts. Too often a missed approach or balk landing was not considered or attempted. In a number of cases, landing performance was compromised due to the aircraft landing long. And post-touchdown, the recorded actions of the crew were often non-standard, and more often than not, the accident crew were subjected to a sudden reduction in visibility which they had not anticipated properly and with which they were not prepared to deal. In spite of all the warning signs evidenced by these conditions, the crews of these accident flights were confident in their ability to perform a safe landing, with the decision to continue the landing after the runway environment being lost, often being the final condition leading to the accident itself. In this situation where visual cues diminish or disappear after the decision to land has been made, the first feeling or impression on the part of the pilot is one of incomprehension, followed by a period of inaction where he or she is often left wondering what's just happened. During this void of inactivity, there's often an anticipation of the original conditions returning. An explanation for such inaction is the fact that at that very moment, while awaiting for the runway environment to reappear, the brain becomes task saturated, unless the pilot has been trained to react instinctively and immediately to the threat. The Transport Canada investigation team believed that there was a case for stating that in their opinion crews need to be more acutely aware that an approach near convective weather is a hazardous situation to begin with, and must acquire a better understanding of all the conditions that they may experience in final approach. They stress that each should be ready to conduct a missed approach at any time one of these conditions escapes their control or understanding. Never should they get themselves into a situation where the missed approach option is no longer available. In the story of Air France 358, a number of the developing conditions mentioned here escaped the crew's understanding and therefore control, even from the very early commencement of the approach. In retrospect, the conditions did warrant a decision to divert, long before it was finally felt by the captain that discontinuing the approach and overshooting was no longer a viable option. In this context of appropriate decision making, the investigation team also commented On the Air France procedure at the time, whereby this very decision on whether to discontinue the approach or not was at the time delegated to the sole discretion of the captain, regardless of who was actually flying the aircraft. The first officer had a responsibility to suggest a missed approach if he or she deemed it necessary. However, the final call was the commander's. This procedure, by its very nature, was at odds with many other operators at the time, whose logic was that, where responsibility for making the go-around call was equally shared between both crew members, the likelihood of an unsafe condition developing was reduced and thus overall flight safety improved. On foot of Transport Canada's observations and recommendations, Air France subsequently amended this procedure, falling in line with most other significant operators of the day. In their analysis of what happened to the 340 after it left the paved surface of runway 24 left, the investigation team noted that the integrity of the fuel tanks was compromised once the aircraft crossed Convert Drive, the service road off the departure end of the runway. Once the fuel started leaking, the inboard engines or sparks from metal-to-metal contact most probably ignited the fuel. Alternatively, hydraulic fluid leaking from the landing gear may have provided the initial fuel and the overheated brakes the ignition source. There was no significant fire before the aircraft reached the ravine, but when the aircraft stopped, the fire intensified, with the leaking and pooling fuel providing an abundant supply to feed the fire. Initially, the fire was in the wing roots and did not directly involve the fuselage. However, the intensity of the fire grew while the evacuation was in progress, and shortly after the completion of the evacuation, the fuselage was engulfed by flames. The cabin furnishing, carry-on luggage and cargo hold contents sustained the fire, while the dilution of the firefighting foam agent by the heavy downpour acted in a manner to reduce its efficiency. One quickly identifiable source of smoke ingress into the cabin was through the open cabin door at position 2 left. You'll remember that the crew reported that the door had opened by itself during the aircraft's violent deceleration. The investigation team, however, could find no plausible explanation as to why this should have been the case. The possibility that something might have hit the outer handle to trigger the opening of the door while the aircraft was crashing through fences and guardrails and sliding into the ravine through shrubbery was assessed. It was considered unlikely that this had happened because the outside handle is recessed and there was no indication of mechanical damage to the handle or to the door in the handle vicinity. In addition, when the outside handle is activated, the slide deployment is automatically disarmed. Since the girth bar was found in the door sill and the arming lever in the arm position, it's reasonable to conclude that the door was not opened by way of the exterior handle. Consideration was also given to the possibility of cabin trim in some way or another dislodging the interior handle from its position. However, after extensive examination, this was also considered extremely improbable. In short, therefore, many hypotheses were studied to try and establish exactly how this door came to be opened at a time when the aircraft was still in motion, but in the end, none could be proven. What the investigation did, however, conclude was that the inner door handle simply had to be raised in order for the door to open. How this handle came to be moved ultimately could never be determined. The upright brace position illustrated on Air France safety information cards was not a recommended brace position in the United States and Canada, nor was it recommended by a number of other respected aviation regulatory authorities. Safety studies showed that it did not provide adequate protection against flailing or secondary impact injuries. Moreover, depending on the occurrence circumstances, passengers bracing in this manner may actually be at greater risk of incurring spinal injuries. Some of the cabin stowage compartments and curtain rods opened or detached during the impact sequence. Carry-on baggage and other items spilled into the cabin, potentially injuring passengers and creating debris in the aisles leading to the emergency exits, thereby impeding egress. The investigation team presented research that showed that during evacuations, the safety of passengers and crew continues to be jeopardized by passengers, approximately 50%, who prioritize retrieval of the carry-on baggage before evacuating. There are at least two identifiable factors that influence this type of behaviour. The first is the human propensity for affiliative behaviour in emergency situations. Affiliative behaviour manifests itself as passenger movement towards the familiar, most commonly displayed as passengers collecting carry-on baggage from overhead bins in the case of trains or aircraft, or by returning to their cabin in the case of cruise ships, for example, in order to collect valuables and personal belongings before evacuating. A second contributing factor is inadequate provision of safety information. In fact, many passengers may be genuinely unaware that they're not supposed to evacuate an aircraft with their carry-on baggage in tow. Research has shown that less than half of all passengers ever look at or read the safety information cards provided by the airline. Although cabin crew shout to passengers to leave their carry-on baggage behind during emergency evacuations, this information is provided at a time when passengers are highly stressed and the noise level in the cabin is likely fairly high. Not, in all honesty, an optimal time for understanding or adhering to critical safety information. The lack of emergency power after the aircraft came to rest rendered the PA system inoperable, introducing the risk that the onset of the evacuation would be delayed, jeopardizing passenger safety. This risk was particularly significant because the aircraft was on fire. Given that the PA system and the evacuation alert system were supplied by the same emergency power source, the evacuation alert system also failed to activate. The investigators thus suggested that a different power source for each system and a less vulnerable emergency power supply, given that the power source for both are co-located in the forward avionics bay, would in the future increase the chances that the PA and the emergency evacuation alert systems would continue to operate after such a survivable crash. In hindsight, one of the more obvious questions which presents itself is, why were aircraft actually landing on 24 left in the first place, given that of the 5 operational runways at Pearson, it's the shortest of all 5? Well, as is the case with most aviation accidents, there's seldom a single straightforward answer. Over the course of the afternoon, the designated arrival runway had actually changed a number of times. At the time of the accident, runway 24 left was in use because other aircraft had been refusing runway 23 on the northern side of the airport because of the proximity of storms to its approach, and runway 24 right was not available because the ILS had been struck by lightning and had become unserviceable at approximately 1856 Zulu, just over an hour before the accident. That said, the ILS for 24 right was actually checked and declared serviceable at 1944 Zulu, just over 15 minutes before 358 touched down, although there was no indication that the tower controllers were aware of this fact. 358 had been told by ATC at 1933 Zulu to expect runway 24 left and was given vectors for that runway. Furthermore, because a number of preceding aircraft were all cleared for the approach to runway 24 left, no action had been taken to change operations to runway 24 right at the time of the occurrence. Runway 23 was active for departures, but there were no departures taking place since ramp and gate operation had ceased at the main terminals due to the red alert. Some of the facilities supporting the ILS approaches to other runways had also been affected by lightning strikes and were unserviceable at various times during the hours preceding the accident. And so it was that 24 left, despite its shorter length, became almost by default the designated arrival runway. All that said, at 9,000 feet in length, nothing would suggest that it was markedly inferior to any of the other alternatives. Admittedly, it was shorter, but in truth, given the conditions experienced by 358, had they executed the landing per textbook and applied thrust reverse and max manual braking immediately after touchdown, with 10 knots of tailwind and no crosswind to contend with, the 340 would have required nearly 10,250 feet to stop, and not many of the other runways on offer provided for those sort of margins. In hindsight, 33 right, aligned more into the wind at the time of the accident, would most definitely have been the best option available, but that simply hadn't happened, largely because conditions had changed very rapidly, and besides, traffic extending hundreds of miles out from the airport had all been sequenced into an arrival flow for 24 left. With regard to the engineering specifications for 24 left, for the first 1,100 feet, or 340 metres from the threshold, the runway remains level. It then slopes down at a gradient of 0.07% for the next 3,000 feet or 903 metres and increases further to a 0.4% gradient for the last 4,900 feet or 1,500 metres. What this means is that for any aircraft landing on this runway from one end of the pavement to the other, there's a downhill drop of just over 21 feet or 6.5 metres. Although well within regulatory parameters, in the context of 358, what this meant was that in attempting to cope with all the environmental factors being thrown its direction, the aircraft was also running downhill, and that certainly wouldn't have helped. A secondary downward incline was also incorporated by design, this time in a direction from the centre line to the runway edge, in order to facilitate water drainage. This being an important design feature, as the runway surface on 24 left significantly wasn't grooved. But significant why? Well, the practice of cutting or forming grooves in existing or new pavement is a proven and effective technique for improving the drainage on some runways, providing skid resistance and preventing hydroplaning under wet weather. Test results demonstrated that on similarly wetted, grooved runways, the transverse runway grooves produce substantially greater aircraft braking friction levels than were shown by the wetted, ungrooved surface data. The data also suggests that the effects of tyre tread wear are secondary to the greatly enhanced tyre pavement water drainage capabilities available on grooved runways. However, in severe rainfall conditions such as were present at the time of landing, a grooved runway may not make a significant difference to the stopping distance of an aircraft, although the consensus would be that even under these extreme conditions, it would certainly help. As is typical of most things in life, though, where there's a pro, there's also most likely a corresponding con. And in the case of the Canadian runways in particular, this is in no small part directly related to the harsh winter weather in this part of the world. As of 2005, right across Canada, only 4 runways nationally have been grooved. This reflects a Canadian policy to employ grooving only where an unusual drainage problem exists. The biggest problem the Canadians have identified is the fact that grooving allows for accumulation of ice and snow in the grooves themselves, which in itself can lead to runway deterioration and the creation of foreign objects on the runway, with the subsequent and real potential for ingestion into jet engines. They effectively see it as swapping one problem for another. The reason airport authorities go to the trouble of trying to install such features is to ensure, as far as possible, the best friction characteristics when the runway is wet. Adequate runway friction characteristics are required for aircraft deceleration, directional control, and wheel spin up at touchdown, with one of the biggest culprits contributing to poor friction coefficients in wet conditions being the accumulation of rubber deposits. Thus, as part of the overall investigation into the accident of Air France 358, Transport Canada conducted a detailed examination of these exact characteristics on 24 left at Pearson. What they needed to establish was whether or not the lack of routine runway maintenance had in any way contributed to the events of August 2nd. Their findings from tests conducted on August 9th, 7 days after the accident, indicated that for runway 24 left, which hadn't been used since the accident, showed an average friction coefficient value for the first third of the runway of 0.78, the second third at 0.82, and the last at 0.75. These readings were well above levels requiring maintenance action, and thus conclusively signalled that rubber deposits on the runway surface were not a contributing factor in the aircraft's overrun, nor, as it happens, were the wheels or components of the braking system, which also passed post-accident analysis with flying colours. But if the runway itself hadn't contributed to the accident, what about the immediate environment surrounding it? You've probably never given it a whole lot of thought, but what lies in and around runways is heavily regulated. But the truth is, different regulations produced by different regulatory authorities can often lack consistency in how they address the same issues. In Canada, legislation states that a runway and any associated stopways shall be included in a strip. A runway strip is defined as an area about the runway intended to reduce the risk of damage to aircraft running off a runway and to protect aircraft flying over it during takeoff or landing. This strip must be extended a minimum of 200 feet beyond the end of the runway, with a longitudinal slope not to exceed 1.5%, meaning that there can't be a significant drop-off away from the runway within this defined area. In the context of runway 24 left, the asphalt blast pad extends for the first 100 feet, followed by another 100 feet of a downward sloping grassy area of approximately 1.5%. This containing part of the approach lighting system for the reciprocal runway 06 right. Thus, the 200-foot buffer extending off the end of the runway for inclusion in the defined strip was indeed present, and in that regard 24 left did comply with the Canadian legislation. With regard the designated width of the strip area, this was defined as having a minimum lateral boundary of 500 feet on either side of the runway centreline throughout its full length. And again, in this context, 24 left was found to be compliant. The Canadian regulations went further, however, and recommended that a runway end safety area should be provided at the end of the runway strip. This area is defined as being symmetrical about the extended runway centreline and adjacent to the end of the strip, primarily intended to reduce the risk of damage to an aircraft undershooting or overrunning the runway. A safe place, if you like, where the aircraft can overrun or indeed touch down short of the runway, where damage to the aircraft can be hopefully kept to an absolute minimum. Among other criteria, it is recommended that the runway end safety area should extend from the end of the strip to as far as is practical under the circumstances, but ideally not less than 300 feet. As the Canadian regulations merely make a recommendation in this regard, there's no obligation on the part of the airport operator to comply. And in the specific context of 24 left, the local topography didn't facilitate such a recommendation. Therefore, despite the fact that industry-wide runway end safety areas are considered a valuable contribution to aviation safety, 24 left at Pearson International was never equipped with one. The general legislative landscape remained as such until 1999, at which point there were some significant changes. Up to this date, the Canadians had been in compliance with the broader, more globally accepted legislation as outlined by ICAO, the International Civil Aviation Organization. However, in 1999, ICAO elevated the status of the 300-foot runway end safety area from a recommendation to a standard. In other words, compliance was no longer discretionary. In addition, they now recommended that the overall length of the runway end safety area be increased from the initial 300-foot value to 800 feet where possible. This obviously caused the Canadians some difficulty, and so, as outlined within the terms of the contractual agreement, they applied and received a derogation. Therefore, despite the change in legislation, a runway end safety area as defined by ICAO is still not formally required in Canada. The United States Federal Aviation Administration, the FAA, conducted a study on aircraft overruns over a 12-year period between 1975 and 87 and found that approximately 90% of all overruns occur at exit speeds of 70 knots or less, and most come to rest within 1,000 feet or 300 metres off the runway end. Therefore, the FAA requires that commercial airports have a standard runway safety area that extends 1,000 feet beyond the end of the runway and is 500 foot wide, essentially mandating the revised recommended guidance from ICAO, unless an alternative means of compliance is established. It's a sad statement of fact, however, that leaving the paved surface at 86 knots, Air France 358 had indeed come to a complete stop within 1,000 feet or 300 metres. Therefore, had the ravine at the end of 24 left been filled in, as was suggested at the time of the legislation change, in order to facilitate a proper runway end safety area, the aircraft may well have been saved from total destruction. But even without taking on board such a complex and expensive engineering project, other alternatives exist which were and are recognised by the regulatory authorities as being a suitable alternative means of compliance. For a moment, let's talk about EMASS, Engineering Materials Arrestor System. EMASS is a bed of engineered materials built at the end of a runway to reduce the potential damage which may be caused by a runway excursion. The construction consists of a high-energy absorbing material of selected strength, which will be reliably and predictably crushed under the weight of the aircraft. As the aircraft rolls over the designated area, it is slowed by the loss of energy required to crush the EMASS material, in a similar manner to the concept of a racetrack gravel trap. It is intended to stop an aircraft that has overshot a runway when there is an insufficient free space for a standard runway end safety area, such as runways built very close to water, steep slopes, or areas of high population density, including residential areas or busy highways. Across the globe, EMASS systems have been installed at 15 different locations, including airports in China, Spain, Taiwan, Norway, Saudi Arabia, France, Japan, Germany, and Brazil. However, it's in the United States where EMASS technology is most prolifically utilized, with 112 runway ends at 68 different airports incorporating the system. One such example is Key West's Runway 09, as shown here, where the EMASS installation successfully stopped a Cessna Citation, which overran the runway on landing due to a total brake failure. The system did its job, resulting in no injuries to those on board and only minor damage being sustained by the aircraft itself. Despite the limitations imposed by the topography surrounding Pearson's runway 24 left, EMASS was never, and to this date in 2022, has never been installed on this or any other runway in Canada. One can only surmise that the outcome of the Air France 358 story may have been quite different had the airport operators made some different choices. The truth of the matter, however, was that 24 left was compliant with the Canadian airdrome standards and recommended practices of the time, in that it was designed with a strip 60 metres beyond the end of the runway, free of non-frangible obstacles, and graded in order to reduce the risk of damage to aircraft during an overrun situation. Although there was no runway end safety area required or published for 24 left, no non-frangible objects existed along the path followed by the occurrence aircraft until a distance of 150 metres from the end of the runway. This established a de facto safety area which actually exceeded the standards which was then required by the Canadian legislation by a factor of 90 metres. Regardless, the investigation revealed that it was the terrain beyond this point that largely contributed to the damage incurred by the aircraft and the injuries to the crew and passengers. It was revealed that there were other similar runways in Canada for which similar conditions existed. Such runways, although compliant with the regulations of the time, included hostile terrain beyond the 60-metre overrun area required by the standard. The board believed that all such runways could benefit from a runway end safety area built not with Canadian legislation in mind, but in accordance with the ICAO, the International Civil Aviation Organization, Annex 14 recommended practices, or the FAA's runway safety area standard, both of which would be considerably more conservative. This safety action would remove all non-frangible objects and create a surface graded so as to reduce the risk of damage to an aircraft up to a distance of 300 metres beyond the end of the runway, 5 times the distance which the Canadians were legislating for. In making such a recommendation, the investigation board was acutely aware that the requirement of a 300-metre runway and safety area would undoubtedly affect many of those existing runways, particularly those located adjacent to natural obstacles, local development and/or environmental constraints, which would make the construction of such a safe area impractical or outright impossible. In such cases, the investigation board thus suggested that alternative means of compliance, such as the use of an engineered material arresting system, or EMASS, be examined in order to provide a level of safety equivalent to ICAO's 300-metre figure. Therefore, in the final report, the investigation board made the following recommendations to the Canadian Department of Transport: that they require all Code 4 runways to have a 300-metre runway end safety area or a means of stopping aircraft that provides an equivalent level of safety. Within 1 week of the crash, cash payments ranging from between €800 and €2,800 were given to passengers for interim emergency use. These payments were independent of the claims process, which had been started for passengers who had not retained counsel. It was expected that the insurers of Air France would pay for all damages, as well as extra compensation for having passengers go through the whole ordeal. However, only amounts of between €6,000 and €9,000 had been offered, prompting many of the remaining passengers to likewise pursue legal courses of redress. After a lawsuit lasting 4.5 years, Air France settled the compensation lawsuit with 184 of the 297 passengers on board Flight 358. The compensation in total amounted to just over €9 million. Air France would pay just over $7.5 million and would in return be released from any further passenger claims stemming from the incident. Airbus and Goodrich, the companies that made the emergency evacuation system for the aircraft, would between them pay the remaining $2.5 million. A Vancouver law firm representing the claimants said passengers seriously harmed with either physical or psychological injuries would be eligible for the maximum payout of €135,000, while passengers who weren't seriously harmed in the crash would receive the minimum payment of between €4,000 and €8,000. From Air France's perspective, in June 2008, almost 3 years after the accident, it filed a lawsuit against the Greater Toronto Airports Authority, NAV Canada, and the Government of Canada for approximately €140 million. In the statement of claim filed with the Ontario Supreme Court of Justice, Air France alleged that the GTAA had failed to provide a safe environment for the conduct of civil air operations. The statement also claimed that the overrun and the consequent injuries to persons and damage to property were caused solely by the negligence of the defendants. Air France further claimed that Transport Canada was negligent by not implementing the recommendation of a coroner's inquest into a similar 1978 crash at Toronto Pearson, which had also urged the creation of a 300-metre safety area to give aircraft more room to stop after landing. Eddie Ho, one of the passengers on board Flight 358, sold the photographs he took of the evacuation to media syndicates, earning him a fair bit of money. He won the Canadian Press Picture of the Year for one of them, and it was listed as one of the best photos of the year by Time magazine. The Canadian investigators referred to the pictures in the report and were able to draw some conclusions based on what they saw. However, alongside the acclaim, there was also some criticism. Mark Rosenker, acting chairman of the NTSB, said that the idea of taking pictures during an emergency evacuation was irresponsible. Your business is to get off the airplane. Your business is to help anybody who needs help. In the same way that stopping for your bag can cause unwanted delays, trying to take a picture can slow down the evacuation too, and in this sort of incident, time is of the essence. Likewise, Helen Muir, aerospace psychology professor at Cranfield University in the UK, pointed out that in most crashes, there's only about 2 minutes from the first spark to the point at which conditions in the cabin are not survivable. It's not the kind of risk you want to take. First Officer Frédéric Noud, following a 3-month suspension, returned to operational duties with Air France, while Captain Alain Rosset, as a result of injuries sustained during the accident, would befall the same fate as his aircraft, insofar as neither would ever fly again. This is the complete story of Air France 358, the Toronto Miracle.